Hello everyone and welcome back. In this video, I'm going to talk about sequences that looks like a composite function. Here's a perfect example. Okay, now what I'm going to do first is I'm going to rewrite this general term of the sequence so that it looks like a function. Basically what I'm doing here is I'm replacing n by x. The reason is that this is what we are familiar when I say a function, right? Because the variable is x here. Okay. Now this is a composite function. What do I mean? Well, you can think this as a function inside another function or a combination of two functions, right? I mean, think about this. This is a combination of both sine x and x pi over x plus 1. Inside sine function, you have x pi over x plus 1. Now, working with composite functions can be very complicated. Now, if you think about the sequence, to find the convergence or divergence, you have to take the limit of the sequence, right? There's no way around. So taking the limit of a composite function can be another complicated thing. All right, so what can we do here really? Now let's pause a minute and think about this sequence. If you carefully think about this sequence, imagine if you didn't have that sine term. Imagine if you only had what you have inside this sequence, like just n pi over n plus 1. Now taking limit of n pi over n plus 1 is super easy. What's the limit? Limit is going to be 0, right? That makes your life very easy. But unfortunately, this is not the answer because you have that sine function outside or covering this n pi over n plus 1 term. So how can we find the limit of this entire thing? Here's what I'm going to do. Pay attention, okay? So I want to find the limit of sine n pi over n plus 1, which is a complicated thing. But I know I can find the limit of what's inside this entire function. So what I'm going to do is I'm going to move the limit inside to the function. Now this is a nice little neat trick, okay? See what I'm going to do? I'm moving the limit inside to the function. Now what's the effect here? What's the effect of this here? Think about this. Now we know what's the limit of this inside part, right? It's something that we can easily calculate. We already saw that you can forget about sine and just focus on what you have inside and take the limit of the part that you have inside, right? So what's the limit? The limit is 0, okay? Limit of what you have inside is 0. So now it's covered by sine. So you just need to evaluate sine at 0. Then what is sine 0? 0. And then guess what? The limit of this entire sequence, that look like a composite function, the limit is 0. We found that by moving the limit inside to the function. As I said, it's a nice little neat trick. But however, you cannot use it every time whenever you have any composite function, okay? You have to be careful. So when can you use it or when you can't use it? Here's how you determine that. First of all, okay, no matter what composite function you have, move that limit inside. Do this part, okay? Try to get this answer, this step, sine 0, the step that I got sine 0, okay? Or in other words, move the limit inside to the composite function and find the limit of what you have inside, okay? And then the last thing you want to check is that you want to check whether the function that's outside is continuous at the limit value of what you had inside. So basically, at this point, I should pause my work and I should ask a question from myself. The question should be, is sine x continuous at 0? Of course, the sine function is continuous everywhere, right? So sine x is continuous at 0. So then you can go ahead and evaluate sine at 0 and find the limit of the entire thing, okay? All right. So this is the nice little trick that you can use to find the limit of a sequence that looks like a composite function. Now I'm going to give you 3 more examples plus an example of a sequence which this trick fails. Okay, so let's go ahead and see the second example. All right, so here's my second example. Pause the video and give it a try if you like. Okay, so to find the convergence or divergence, again you have to take the limit. So limit of ln 1 over n. Now this is a composite function. Inside natural log term you have 1 over n, a function inside another function, right? You can think a sequence as a function. Of course sequence is a function. Okay, but anyway, now what we can do is, as I explained in the previous example, you can move the limit inside to this sequence. Now ln, what's the limit of 1 over n when n goes to infinity? Limit is 0. Okay, now you have to pause here and think whether natural log, the function natural log x is continuous at 0 or not. Well, what do you think? No, natural log x is not continuous at x is equal to 0, because natural log x is not defined at x is equal to 0. Hence, you cannot use the trick. Okay, so this is an example where the trick fails. Okay, how do you know whether it fails or not? As I said, first move the limit inside. Find the limit of what you have inside and then decide whether the function is continuous at that limit or not. Okay, now if you want to learn more about continuity, or if you want to refresh about what does it mean to be what does it mean for a function to be continuous, check on the link that appears here on the video, on the top of this video, and it will give you a quick refresher of what a continuous function means. All right, so this is an example where it fails. Now to find the limit of this sequence, you have to use a different trick. I'm not going to do that here. Let's move on to example 3, and at the end of this video I will show you how to find the limit of this sequence using a different way. Okay, because I want to save time, first I want to show you how to find the limit using this trick that I have taught you. Okay, here's example 3. Now as I always say, pause this video and give it a try and then compare with my answer and procedure. Now, is this a composite function? Yeah, you can think it as a composite function. Okay, so you want to find the limit of this sequence where it's square root of n plus 3 over 36 n plus 3. Now what you can do is you can move the limit inside to the square root. Okay, so I'm going to take the limit inside to the square root, and we want to find the limit of n plus 3 over 36 n plus 3. Right, now how can we find the limit of this rational term? Well, now we know how to take the limit of that rational term, right? So if you want to take the limit, what I'm going to do is then I'm going to factor the highest power of numerator and denominator, the term with highest power, right? So in the numerator, the term with highest power is n. Okay, so when you factor n, it's 1 plus 3 over n. When the highest the term with the highest power on the denominator is n, so let's just take n out, so it's going to be 36 plus 3 over n. So n cancel out, so what do we have here? So limit of a square root of the limit when n goes to infinity of 1 plus 3 over n divided by 36 plus 3 over n. So what's the limit here? So when n goes to infinity, 3 over n approaches 0. Same here on the denominator, right? So what do we left it? So the limit of the entire thing, I mean what you have inside is 1 over 36, because the numerator is 1 plus 0, denominator is 36 plus 0. So the limit is square root of 1 over 36. Is the function square root continuous at is the function square root x continuous at 1 over 36? Of course, you can take the square root of 1 over 36 easily, which is 1 over 6. Okay, so the limit is 1 over 6. So this is an example where our trick works. So the limit is finite, hence this is a convergent sequence. Okay, example of a convergent sequence. Alright, so let me give you another example. Alright, here's my next example. Now this can be a little bit challenging. Now, before I take the limit of this sequence, of this general term of the sequence, what I'm going to do is I'm going to rewrite it using logarithmic rules. Now, when you have subtraction in between two logarithmic terms, what you can do is you can combine them as division. Okay, now this is basic logarithmic rules. Now this helps a lot in our problem. Okay, all right, so remember, log a minus log b is same as log a over b. This is a logarithmic rule. All right, now we want to take the limit of natural log 5n square minus 1 over 2n square plus 3 when n goes to infinity. Now, as I said before, this looks like a composite function, so let's move the limit inside. Okay, so then you just need to take the limit of 5n square minus 1 over 2n square plus 3. Now we know how to find the limit of this term that looks like a rational function, right? So how can we take the limit? Well, we just need to factor out the highest power, term with highest power in numerator and denominator. So in the numerator, it's n square. So I'm going to take n square. You can just leave 5 inside. So 5 minus 1 over n square. In the denominator, it's n square again. So you can have 2 plus 3 over n square inside the parenthesis. Okay. Now, obviously, you can see n square cancel out. So natural log limit n goes to infinity. What's left is 5 minus 1 over n square, 2 plus 3 over n square. All right. So what happens to this term when n goes to infinity? 1 over n square approaches to 0, right? 3 over n square approaches to 0. So what's the limit? Natural log, in the numerator, it's 5 because 5 minus 0 is 5. In the denominator, it's 2 plus 0 is 2. So natural log 5 over 2. Now you have to pause at this moment and ask the question, is natural log x continuous at 5 over 2? Of course, yes, it's continuous at 5 over 2. So hence the limit is natural log 5 over 2. It would have been nice if we can get the numerical answer, but I'm not going to use my calculator. I can leave my answer like this. So this is a finite number, by the way. Hence, again, this is a convergent. This is a convergent sequence because the limit is finite. Okay. All right. So at this moment, what I'm going to do is I gave you several examples where the sequences looks like a composite function, and we saw one example where this trick failed, right? So the sequence was ln 1 over n. Now let me show you how I can really find the limit of ln 1 over n. Now what we can do here is we can use a logarithmic trick. Okay, so I'm going to rewrite ln 1 over n as ln n to the power minus 1, because 1 over n is n to the power minus 1, right? If you take that n to the numerator. Now using a logarithmic trick, I can take minus 1 in front of logarithmic function. So it's negative 1 ln n. Okay, all right. So that's a logarithmic rule. So this sequence is basically negative ln n. Now what's the limit when n goes to infinity of negative ln n? Oops, not ln x, ln n. Now I'm going to take that negative outside. So you want to take the limit of just ln n. So what happens to the natural logarithmic function when n goes to infinity? This part goes to infinity, right? It gets bigger and bigger. So the limit here is infinity. With this negative, it's negative infinity. Okay, so the limit is infinite. Okay, so then this is a divergent sequence. Okay, see, we cannot use that trick that I taught you in this video, but you can use a different method to find the limit of this sequence. Okay, so if the trick fails, you have to find a different technique. All right, so thank you very much. I'll see you in the next video.